Welcome back. So we come to the very final part of the lecture. And this is about another method for learning graphical models, but it's a non-probabilistic version, and I'm going to tell you what I mean by that. So we already saw in the previous part of the lecture about energy minimization that probabilities didn't occur at all, right? We just said the maximum of the probability is this minimum of the energy. The energy is a sum that is much more convenient to work with than a product. So let's just think about energies, let's think about summation of terms, and let's forget that there was ever a probability involved. So structure support vector machines follow a similar direction. So they tried learning an energy function directly without going through, for example, the maximum likelihood principle. So we are still working on the supervised learning problem. We're given training examples. The difference is now we have to know our loss function already at time of learning. For graphical models, for conditional random fields, first you learn the probability distribution, then you use it to make predictions using a loss. This kind of learning here with structured SVM, it needs to know the loss function already at training time. Okay. So how would we make predictions? Well, we can learn an energy function and say the prediction should be whatever minimizes the energy function. And we saw that minimizing an energy function is possible under certain configurations, maybe even easier than doing doing kind of probabilistic inference in a probabilistic model. For some historic reasons, we will not minimize an energy function. We will instead maximize a compatibility function, which is the negative of the energy, just because the textbooks are typically formulated in this way. I'm sorry for that. People cannot agree on the sign. So I will talk about a function of x and y, which is large if its combination of x and y is good, and is small if the combination of x and y is bad. And that means it's exactly the negative of an energy. In an energy, small is good, here, large is good. That's it. Okay, so how would we learn an energy that that works well for these kind of predictions? Well, we still parameterize our energy as a linear function of some feature map and a weight vector, so it's still a function. That's good. We make predictions by maximizing it. So it's not an energy anymore, sorry, it's a compatibility function. But the negative sign doesn't play a role. We can just absorb it in the W. So we made prediction by maximizing it. So what weight vector should we choose? Well, we saw that the ultimate goal of learning is to make predictions that have the minimum expected loss, right? So that is the expectation over the data, the true data distribution out there of our loss, making a prediction f of x for where the correct output is y. Well, that's the risk. So if we can find a function f that has the minimum expected loss, well, we would have found the perfect classifier. It doesn't get any better than that. We know that this is the optimal classifier under the data distribution of the world. So taking this kind of view, directly going for a function that has the minimum expected loss, well, it has the advantage that we really optimize for the quantity of errors of interest, small loss. We don't care about maximum likelihood of the data if what we really care about is minimizing the loss at prediction time. Another nice thing is that this partition function that needed summation over exponentially large stage spaces will not even show up. So we avoid that problem completely. The disadvantage is, well, we need to know the loss function, otherwise we cannot talk about the expected loss. That might not be a big problem. But also, we cannot use probabilistic reasoning for finding the best W. So we cannot, we can still talk about expectations, but we cannot talk about maximum likelihood, map estimation, and so on, because, well, we now don't define a probability distribution anymore. We only define this compatibility function. Okay, so what can we still do? The real goal, minimize the expected loss of our prediction function f over all parameters w. Once we know w, the function f is completely determined. Two major problems in this. We don't know the data distribution, the true distribution of the data in the world out there. So we cannot compute the expectation. And second, even if we could compute the expectation, this function f is a really nasty beast. So it outputs a structured prediction which is in some discrete space. So it's a piecewise constant function of my parameters. For some parameter range, it will output one value, eventually it will switch to another value. There can be nothing in between because the output space we predict is discontinuous. So it will just have some value, and then at some point it will jump to another value. Piecewise constant. That's the worst thing you can hope for when you try to optimize something, because locally you can't tell anything, and you also have no clue how good you are, because you cannot take a global view at the picture. So we cannot apply gradient-based optimization. So that is not a very promising situation to be in. So we're going to replace both of these in the standard way of regularized risk minimization. First problem, the data distribution is unknown. Well, instead of the actual data distribution, we work with the empirical estimate based on the training data. So instead of taking expectation, we take the average over the training data. And as also you might have had in the pattern recognition course and so on, that might overfit if your model class is too rich. So we will also add a regularizer to that system. So the norm of the weight vector with a constant in front, and that will prefer solutions that have short weight vectors and that are less likely to overfit. So what we end up with is a regularized empirical risk. It's the norm of the weight vector squared as a regularizer plus the average loss of your training data. And this we can now compute. We know our training data. We know our loss function. So this would be a computable quantity. Okay. But it's still a discontinuous quantity with respect to the weight vector. So it's still that the argmax here will either give you one value or another value, but nothing in between. So it's still a discontinuous function, so we still cannot use gradient descent or so to find it. So people came up with a nice trick. Instead of this delta function of two arguments that measures exactly the loss for a discrete prediction, you replace it with a surrogate loss function L, which is an upper bound to the true loss. At the same time, it should be continuous and convex with respect to the unknown parameter. Why is that a good thing? Well, if we replace our loss with the upper bound on the loss, then we will get a function that is an upper bound to the original function we care about. If we can minimize this guy, we know that the true thing is smaller or equal to what we minimize. So if we get a solution with a really small value here, it will automatically also have a small value there. So often if you want to minimize something difficult, if you can find an upper bound that is easier to minimize, you will be able to at least get some good solutions also for the difficult function. By choosing this curly L as continuous and convex with respect to the unknown parameter, that means we will afterwards have a convex optimization problem, and we will be able to use gradient-based techniques because it's continuous and so on. So this is what we end up with. We will have to minimize sum over our training data of a loss function that we'll have to specify in a second, plus a regularization term. So what kind of loss functions can we put there? In a sense, the easiest you can do is the so-called structured hinge loss. And that leads to structured SVMs, as I will talk about in a minute. So this is a tricky situation. So we will take as the loss for any weight vector and some input-output pair the maximum over all possible labelings of the following expression. You evaluate how far away your loss, the label that you currently look at, is from the ground truth label, and then plus two linear terms, one which is the inner product of my weight vector with the ground truth features, and one which is the inner product of my weight vectors with the any other labeling that currently is in this maximization. It's not at all obvious what that is, but you can show that this is an upper bound to the delta itself, because this guy can never be less than 0, right? Because it's the maximum over all y's minus one specific guy. So it's an upper bound on the delta. At the same time, it's the maximum over many linear functions with respect to w, and the maximum over linear functions is a continuous convex function. So we have achieved an upper bound to the original loss that is continuous on convex. That's good. So we'll see how that looks like in a second. There's alternatives you could do. You don't have to do this hinge loss. For example, you could do so-called logistic loss. Logistic loss, you wouldn't take the maximum over all states. You would take the sum over all states. And instead of the maximum over this difference, you would take so-called softmax. So it's the exponential of this difference summed over all possibilities, and then the logarithm outside again. So this is also differentiable. It's convex. Strictly speaking, it's not an upper bound to delta. Delta doesn't even show up here. But there's variance where you squeeze this in, and I mean, that is not the biggest problem. So why did I include this? Well, if you look at what these terms are, we will recover our conditional log likelihood from the conditional random field. So the loss I just showed you, the logarithm summing over all terms exponential of minus these differences, which by itself is not particularly obvious. Well, this part here doesn't depend on the y, right? So exponential of minus this is just the constant with respect to the summation. We can move it outside of the summation. Then we can take its logarithm, and we end up with something we already know, sum over all training examples, this linear term over all training examples plus logarithm of the sum over all states exponential of what used to be our energy. This is exactly the conditional likelihood that we had in this CRF learning before. So we can also derive the full conditional random field stuff we did before. It's just a special case of this loss minimizing training. Well, in the following we will look at this one, the structured support machine one, but keep in mind that the difference between support vector machines and conditional random fields is really not a big one. So sometimes people argue that one is the right one and the other is wrong, or vice versa. They are very, very similar. You can interpret one of them as a hard maximum over all configurations and the other as a soft max over all configurations. So it's not a big deal. Okay, so let's be a little bit more concrete and look at some examples. So so one example people have done for this is if you just want to classify an object into multiple classes. So it's not even a structured object, it's just one output variable and it has multiple states. What would you do? You would define your output as just the number of states. You would define your loss function as 1 if you predict the wrong class and 0 if you predict the right class. And now you have to define a feature function that looks at your input and all possible outputs at the same time. And you can do that by just computing a feature of your inputs, image features if you want to classify an image. And you stack them and you put them in this stack to the location of the label you're currently interested in. If you're interested in label 2, you put this to the second block of your long vector. If you're interested in label k, you put it in the end. Your weight vector will also have this form, so you will have part of the weight vector which looks only at labels in the beginning, and part of the weight vector looked at all of the others. Now you write down this minimization that corresponds to your training of a structured support vector machine. And what you have recovered is a classical multi-class classifier by Kobe Kramer and Jora Singer called the multi-class SVM, Kramer-Singer multi-class SVM. So I included this because it shows you a little bit of what this loss function does. So what is this loss function? It's the maximum of a lot of terms, and each term is either 0 if you're predicting exactly the right label. So if you predict the right label, the y will be yn. That means this term and this term are the same because y is yn. And the loss of predicting the right thing is also 0. So this will just be 0 if you predict if your maximum is the right thing. Otherwise, it will be the difference between what you predict for the ground truth and what you predict currently plus 1. So in order for this loss to be really small, you need that the prediction on the correct label is bigger than the prediction on any other label plus 1. So you enforce that the value you will predict on the correct label of the training set is the biggest, not just a little bit, by a whole margin bigger than the values you get on all the other possible classes. So you make sure that the scores of your compatibility function, the correct one is on top, all the others are far away at the bottom. That creates a very robust setting. So if you enforce on the training set that the correct ones are here and all the wrong ones are far away, you have a good chance that at prediction time you will also have the correct one on top and the other ones at the bottom. The nice thing about this structured SVM setting is that you can easily expand it to many different settings. So for example, imagine you want to do multi-class classification as before, but your loss function is different. So instead of saying it's equally bad to predict this label or that label, maybe you want to have hierarchical loss. So if the true label is cat, but you predict dog, well, that's wrong. You get an error. But if you predict bus, well, that is really, really wrong. So you want to have a larger error for that. So it's essentially classification where the loss is given by a tree structure and the distance within the tree is your loss. How could you incorporate that into an arbitrary classifier or even a conditional random field? I don't know. But in the structured SVM, the loss pops up really explicitly. So you just plug in this loss into the objective. And what you will get is that it will try to make the correct label, let's say cat, bigger than all the others, at least bigger than all the dog labels by 1, but it will make the cat label 2 bigger than the car label. So it would push the not so bad errors far away, but the really bad errors even further away. So that way it will, at prediction time, hopefully, if it makes a mistake, only make a not so bad one and not a really, really bad one. And so on. You can construct all kind of prior knowledge you have about your loss or about your features. You can plug it in here directly and you will get a solid, well-justified learning algorithm that fulfills, hopefully, these properties. Okay. Secondary structure prediction, we had that as an example. What would we do? We would have inputs which are strings over the alphabet, outputs which tells you which input binds to which output. You have to define some domain-specific features. What would be your loss function? Well, you just count how many correct or incorrect bindings you predicted. All of these are relatively straightforward once you know how to represent your data, and you can minimize your training objective of a structured SVM.
Is binding energy a physical energy or probabilistic energy, or are they the same?
This would most likely be the physical energy that you can plug in, or at least, or you might make it an arbitrary unknown indicator and you learn the corresponding energy from data. Both would be possible.
Corresponds to the energy function.
No, yes, this is not the energy function because the energy function is half an hour ago. Now it's a compatibility function. This is not the energy of any kind of graphical model. This is the physical repulsion and so on. Yes. Thanks for noticing. Sentence parsing, same thing. We can directly put in the loss that we have in sentence parsing, like the number of wrong assignments and so on. So we know what we want to minimize. It's this sum of losses plus a regularizer. How can we do that? Well, the first idea we can have is it looks like a conditional random field, so we can also train it like a conditional random field. We can do gradient descent on this. Well, not quite, because it is continuous, it is unconstrained, it is convex, but it is non-differentiable. Why is it non-differentiable? Well, because you have linear functions, and the maximum over many linear functions is not differentiable. So we cannot use gradient descent, but we can rely on so-called subgradients. So if you haven't seen subgradients before, they are really cool. A subgradient is a generalization of a gradient, and it's defined as a vector such when you take the inner product at a certain location W0 of the gradient that you think is a subgradient with the difference vector, any location to your current, you get a lower... This is a linearization of your function with slope v. The linearization of your function with slope v has to be below the actual function itself. So this generalizes the gradient, the slope of the function v. This is an example of a slope of a function such that the linearization of the function lies below the graph of the function. So this is a valid subgradient. Here's another slope of a function that is also below. So this is also a valid subgradient. The subgradient at the location is might not be a single element. It can be a whole subset of legal subgradients. This is also one, by the way. Why is it that I say it's a generalization? Well, if you are in a differentiable position, then you know that the only linear function that lies always below a convex function is the one given by the gradient. So if you are at a differential position, there's just one subgradient, and it's actually the gradient. But if you're at a non-differential position like here, like at this kink, you might have multiple. Nevertheless, you can use these subgradients also for optimization. And the procedure is essentially the same as gradient descent itself. So you start with some initialization, and then you repeat until convergence or until you're happy. Compute any of the subgradients of your function. It's not unique, but any will do. And then walk a little bit in the opposite direction of that subgradient to update your weight vector. And they do that until your function value doesn't change anymore. So it's an iterative update, the same as gradient descent. You always go in the opposite direction of what the gradient subgradient tells you. In contrast to gradient descent, you have to be a little bit careful because, first of all, subgradients are only defined for convex functions. If you have a non-convex function, your graph might curve down somewhere, and then you will not have any slope that lies always below the function itself. And more importantly, the subgradient method is called subgradient method instead of subgradient descent because it's not a descent method. So the value of the objective does not go down in every step. Sometimes the objective value can go up even though you took a good step. And that is a bit, if you look at numerically and want to decide if you have converged or not, that is a bit annoying because it might go up and then it might go even more afterwards. So numerically it's a bit annoying. And I like this picture to show you why that happens. So imagine you want to do subgradient descent on these level sets, right? So in the middle it's the smallest, out it goes up. These are the level sets of constant value. Imagine you're here. This is a valid subgradient direction because if you look at the linear function outside, it will, or if you would look at a function that is orthogonal to this, it would lie kind of outside. So the level set of the linear function would be outside of the level set of this function. So it's an outer, the linear function lies completely below the graph of the function itself. So this is the opposite direction of the gradient, or just the gradient of the direction. And you see there's no point on this that has a lower objective than where you started. So if you would try to do a line search, you would do 0 distance. You would stay where you are. Nevertheless, subgradient method tells you if you just walk against the gradient for a bit, and you do that every time, you will find the global minimum. Why is that the case? Well, you can actually show that even though the objective value doesn't go down, you come closer to the minimum location. So even though the value here is higher than there, the distance to the minimum has gone down. And if you every time gets closer to the minimum, eventually you will hopefully reach it. So subgradient method is a really cool thing. And it's not the most effective way of optimization, but it's a very, it's one that actually works in practice and is used. So how do we compute subgradients for this objective which we have? So it's the sum over the loss, right? And I now call the loss n as ln for the nth example, so I don't always have to write the summation. So this is some loss function plus some linear function. The ln is the maximum over a lot of possible labels of this component function, and this component function is linear. So how does this loss look like? Well, for every fixed configuration y, it's a linear function. So this is one of the linear functions. For the next configuration y, it's a different linear function, and so on and so on. So you have a whole zoo of linear functions with different slopes, different offsets, and so on. And now what is my loss? My loss is the maximum over those. So this guy is the function that we want to minimize for one example. So as you see, it's had exactly that form. It's nice and convex, but it does have non-differentiable points. So we cannot always compute gradients. Can we compute subgradients? Turns out, yes, it's not so hard. So what would be the subgradient at that location? Well, we go up, we come to a certain point, and we have to find the... so this point is part of a linear function, because every part of the graph is part of a linear function. So this has to also be part of one linear function. Which linear function? The one that has the highest value at that location, right? Because it's the maximum over all y's. So one of the y's must have been the one that had the highest value. So we find which linear function was responsible for this part of the slope. And then we know that the subgradient at that point, since this is a piece of a linear function, we can just use the gradient of the linear function, and we have found a subgradient of our overall function. So how do we compute a subgradient of this complex loss? For any location, find the maximum, the maximum y, and then use the gradient of that. So if you're at a non-unique position, there's multiple linear lines that could be maximal. Doesn't matter, you can use any of them. Any of them will give you a subgradient. So that is quite nice. Okay, so here's the whole training algorithm. It looks a bit longer than the previous, but that's just because I wrote all the inputs and outputs in the end. So you get data, you need to be able to compute a feature map, you need to define a loss function, and you might have to choose a regularization parameter. You have to choose a number of iterations, because the subgradient method, it's not so easy to know when it has converged exactly, so just we pick a fixed number of iterations here. We choose a step size. You can make the step size go down over time, or you can keep it fixed. All of that is optimization course 101. And then you go over all iterations, you go over all examples. For every example, you compute the subgradient. How do you compute the subgradient? You find the labeling that has the maximum score out of all of these loss functions. So each of these loss functions was the loss itself, plus a linear term that depends on the y, minus a linear term that only depends on the ground truth. This part doesn't depend on the maximization, so we can also skip it when we compute the max. So you have to compute the maximum, the assignment that maximizes these two, and then you take the gradient of this function with respect to w. Well, it's a linear function with respect to w, so the gradient will just be this term minus that term. So this is your subgradient. Once you've computed that, you have a subgradient of your function. You update your parameter by going multiple of the step size into the direction of the subgradient, and this is part of the gradient that comes from the regularization constant. So it's the same operations as we had for gradient descent, only now we need to maximize over all configurations in order to find the subgradient direction. So each update of our weight vector needs as many maximization operations as we have examples. What are these updates? What are these operations? If you remember, this was just the form our energy function had, right? So if our features are defined in the same way as a graphical model would have been, like small interacting parts, then doing this guy maximization is just energy minimization. It's exactly what we saw before. You can do leaf propagation if your model is a tree. You can do graph cut if you have this submodular energy. So in this step, we plug in the energy minimization that we have, that we did an hour ago. And that way we can compute a new configuration, update our weights, and so on. Here's a hopefully illustrative example. Imagine we want to segment that image. What is our loss function? Let's say it's Hamming loss, meaning we check for each pixel if we predict the right label or not. And for simplicity, let's assume we only want to segment cows. So we have a segmentation mask. We have only one training example. It's this image with that annotation of the cow. Okay. In the very first iteration, we start with a 0 weight vector because we have to start somewhere. So what do we have to do? We have to, for all training examples, which means for the one we have, find the configuration of labels y such that the compatibility function plus the loss are maximal. This function is linear in w is 0, so this is 0 in this step. So now what we have to find is find the configuration that has the maximum loss with respect to the ground truth. Since we can decide on the label at every location separately, this will be the one that for every pixel decides the opposite of the ground truth. So what we will get is the subgradient in the first step is like the negative image of the ground truth. So all of these background regions, do I have it? Yes. So everything here is foreground, only the cow would have been background. So the worst possible thing you can think of. Now we get a subgradient that is the feature of the ground truth, this one, minus the feature of what we predicted. Thinking of this just as colors, that would mean positive contribution of ground truth, negative contribution of the thing we predict. So we would get more black and white, positive contribution from the cow, negative contribution from what we predicted. So plus green, plus black and white, minus green, blue, gray, and so on. What else is in the background? So that is our first update that we do to the weight vector more black and white, less green, blue, gray. So in the next step, we would now have to solve a minimization which positively reacts to black and white, negatively reacts to green, blue, gray. So it will not do the opposite anymore. It might find a different region. This region again will be subtracted from the ground truth, which will give us a new update to our weight vector. And then after a few steps, it will have found a configuration of weight in the weight vector such that even if we minimize the this objective loss plus linear term, we exactly get the ground truth back. If we exactly get the ground truth back from our subgradient, well, then these terms are identical and there's no more changes, so we have converged. Okay. If you have too much data, what do? Same trick as before. You do a stochastic version of that. So instead of computing a subgradient on all examples, you compute it only on a small subset. And since the direction you go with the subgradient is not always perfect anyway, it doesn't really matter that now you do a noisy version of going in the wrong direction. So you're doing the same step as before, only instead of going over all examples in a sum, you randomly choose a training example and go in the direction of only that one. The advantage is that it's much more efficient. Instead of having to do these energy minimization operations for each example in order to update W once, now we update the W after with only one of these energy minimization argmax steps, namely for the randomly chosen training examples. At the same time, we make less progress per step, so we'll be doing more steps, but each step is faster, so it's the usual trade-off of stochastic optimization. Subgradient methods are known to be slow. Can we do better? And the answer is yes. So because this is a very specific form of objective, we can do other kinds of optimization. I'm not going to go too much into detail, but if you're familiar with support vector machines, we can train the structured support vector machine similar to a regular support vector machine. So we will do a trick. Instead of this objective which has a non-differentiability, we introduce constraints. So we introduce new variables xi, which are essentially the same as our old max, but we just call them a new variable. And then we constrain them to be at least as bad as that, at least as big as the maximum we care about. At the same time, we minimize over them. So if we make them as a constraint at least as big as the maximum, but at the same time as small as possible, well, they will end up at exactly the same as the maximum. And what we're optimizing here is the same thing as before. Only now we rewrite it in a way where the objective function now is differentiable in both unknowns, W and xi. So optimization literature is full of these tricks where by introducing new variables or dualizing parts and so on, you get certain properties shifted to other properties. So here we had a non-differentiability in the objective. Now we have a differentiable objective, but instead we had turned the unconstrained optimization problem into a constrained optimization problem. In fact, what we have is we have one constraint here per training example, and these are nonlinear constraints, right? We have this maximum, and this maximum is a nonlinear operation. Nonlinear constraints are not pretty either. What can we do? Another trick. Instead of saying that xi has to be larger than the maximum of all of these, we can say that for every individual value, the xi has to be larger than the value. So we say that for all possible y's, xi has to be bigger than the individual value, then automatically in the end it's also bigger than the maximum, right? Because one of these y's is the maximum. What have we done? We have replaced the nonlinear constraints, and we have replaced it with a large number of linear constraints. Now, instead of as many constraints as we have examples, we have as many as we have constraints as examples times the number of possible configurations for our outputs. Admittedly, that is a very large number. But we have taken a difficult, non-convex, convex but non-differentiable problem, and we've turned it into something which is a quadratic objective with linear constraints. So it doesn't get much better. It's the so-called QP. There's a lot of literature how to solve QPs. So what can we do? That means we can train a support vector machine with structure. This is almost the same way as a linear support vector machine in general. We write down these inequalities. we can, in order to simplify or make it more look like a normal support vector machine, we introduced like difference vectors. That's not so important. But what we end up with is, let's see, sum over norm of the weight vector plus slacks and one inequality constraint per example multiplied with the number of options. Quadratic objective, linear constraints. Can we just plug this into an ordinary? Well, we could. The problem is these number of constraints will kill us. So if you have 10 to the 50 different constraints, you cannot even write them down, and much less you can feed them to an optimization package. So you cannot just feed them into an ordinary solver, but you can build your own that has very similar properties. And one trick that often makes sense, yes, so the number of constraints prohibits us. One thing that makes sense is the observation that there's so many constraints, not all of them will matter. So if you have an optimization problem of that type, typically there will be a small number of actually relevant active constraints, and then all the others will be fulfilled automatically anyway. The problem is we don't know which one are the important and active ones. So this suggests to use a working set training where you start with a small number, maybe none. You solve for that. And then you check if out of the solution you get, there's still any constraints that are not fulfilled. If there's none that are not fulfilled, you're done. If there are some that are not fulfilled, well, you take them, add them to the constraint set, and resolve. And that way, your constraint set will grow over time, but it will never become 10 to the 50 or so. So this is typical working set training. You repeat until convergence, solve this structured SVM problem with only a subset of the constraints, check if there's any violating constraints, and if yes, add them to the set and reiterate. The nice thing is that this actually gives you some guarantees, so it will converge to the right thing, and you have a guarantee that it will converge at least in polynomial time epsilon close to the global optimum. It's not a very strong guarantee, but at least you know that you do not have to do exponentially many steps to do anything reasonable. Okay, this is the algorithm. I just talked about it. If you know about convex optimization, you can also know about dualization. And structured SVMs are one of the examples which you can beautifully express in dual form and then solve in the dual objective form instead of in the primal. In fact, the dual is much nicer than the primal because now it's really a quadratic function. Our unknowns are now called alpha. It's a quadratic function in alpha plus a linear term. And the constraints themselves are not so bad. They're just inequalities. Very nice. The main problem here is now the number of constraints. I mean, the number of unknown variables has gone up explosively. Nevertheless, these are the methods that currently are maybe state of the art. There's some work by Simon Lacoste-Julien last ICML a few years ago, also by ourselves from CVPR last year, which show very nice, smoothly converging rates for these kind of objectives. So this is one of the directions where currently still a lot of active research on optimization for structured SVMs is going on. Okay. That's my summary of structured SVMs. I could only give you a high-level glimpse. If you look at the tutorial text, you will find more. We have a training set. We have a loss function at training time. We parameterize a linear function with an arbitrary feature map and a weight vector. The goal is to minimize this, to minimize the expected loss on future data. We do that by a regularized risk minimization framework where the objective that we have to solve in the end can be interpreted as find a compatibility function, a weight vector W, such that the output you get from it on the correct training data, on the training data, which is the correct output, has to be larger than the output on any other label, the green stuff, and plus a certain margin that makes sure that bad solutions are pushed away even further than not so bad solutions. So this will give you some nice guarantee, and if you rewrite these terms, you end up exactly with this Hinge loss, which is the maximum over all things. It's a convex optimization, unfortunately not differentiable. I showed you some equivalent formulations that you can use to optimize. And generally, it's a nice properties of this method that since you have an objective function, you can throw all kind of tools for optimization theory or reparameterizations on it, and you know that the solution will still be the one thing you care about. So it's good to have some arsenal of techniques available for these things. All of these structured SVMs need to evaluate many of these argmax predictions, which were the energy minimization steps we had before. And that brings me to the last slide. Thank you. Structured prediction learning, it's full of open questions. How can we speed these things up? How can we use less training data? Can we maybe do semi-supervised learning? Can we use transfer learning? Can we all of the things that are well explored for ordinary learning? Can we also use them in the structured context? There's this big question of if we cannot do approximate inference exactly, can we still minimize our function? If not, what prevents us? Can we maybe come up with alternative objectives that have the same properties? Can we learn the underlying representation, for example, with deep networks, and apply them to real data? Thank you. That's it. I'm out of material. Thank you for making it until the very bitter end. Is there a final question? I know, everybody's overwhelmed and tired. If you do have questions, send me a mail or look at my website. You can, yes, thank you.
What specifically do you do with, like, you develop the algorithms?
Yes.
Or apply them?
I work mainly on the algorithm side. So for example, this optimization method in the dual that was 5 slides ago, I work on like this transfer learning aspect. So how can we share information between multiple learning problems? That's also for graphical models an issue. We do use them sometimes, but typically it's more as an example application. So we use image segmentation. So all of the models I showed you with horses and so on. These are also in combination with deep learning. These are the state-of-the-art techniques for image segmentation. So in that case, it's not really new research on graphical models, but it's using them for existing research and so on. Well, thank you. See you next year.